So quickly, first a couple of definitions related to this. So enthalpy change solution definitions. So the number one is enthalpy of solution itself. It's known as delta H solution with a knot on top. This is the standard enthalpy change. It's an enthalpy change of solution. Now, so standard enthalpy change of solution, and now what it means is that it's the energy that is released or absorbed when you dissolve something. So, or absorbed when what happens when 1 mole of a substance is completely dissolved in water. To form an infinitely dilute solution. To form an infinitely dilute solution. Infinitely dilute solution means that it's just a dilute solution measured under standard conditions. So if I have 1 mole of anything, if I have 1 mole of salt, NaCl, solid, I'm going to mix it in water. And if it dissolves, so if it dissolves, it's going to form 1 mole of aqueous ions. So ionic compounds, they always dissolve. So the enthalpy change or the energy that is released or absorbed is going to be known as the enthalpy of solution for the salt NaCl. Yeah, Vardha, is this clear?
Yep.
Vice versa, if you have 1 mole of a covalent compound like ethanol, then they would also dissolve. You mix it in water. They're going to form strong hydrogen bonds with water, and when they do that, they would be completely attracted to water, surrounded by water, and they're going to mix in water. So they're going to form C2H5OH aqueous, and that's also known as the enthalpy of solution of ethanol. Now, the thing is that enthalpy of solution could be both exothermic or endothermic. So if it's exothermic, what does that mean? That means that the solute particles or there's strong attractive forces between solvent and solute. So that means there's strong bond formation, attractive forces. So it dissolves easily. That's why energy is being released. And it's going to be more soluble at even lower temperatures. Okay, vice versa if it's endothermic. That just means that you're trying to, like, if you're trying to dissolve a salt crystal, like marble does not dissolve, right? Because the previous bonds are very strong compared to the new bonds that are going to be formed. So if it's endothermic, then there's a lot more energy that's being released, and it's it's whatever the particles are, they're not very attracted to the liquid. So you're not going to have strong forces between solute and solvent. So that means not a lot of energy is being released. Instead, energy is being used to break the bond. So that's why it's endothermic overall. So no strong attractive forces between solute and solvent. Uh, energy is needed to dissolve. Which is why it's going to be more soluble at higher temperatures. Okay, is this clear?
Yep.
So that's one definition. Now the other one is there's a thing called enthalpy change of hydration. So this is the standard enthalpy change of hydration. Now, what is hydration? That you've got a gaseous ion, any gaseous ion, and you just mix it in water, and it gets completely surrounded by water molecules, and it turns into an aqueous ions. So it becomes Na+1 aqueous. So visually, it's something like this, that you've got a. I mean, visually, it's something going to be like this, that you've got a sodium ion. So sodium ion, let's say, I've got a circle. That's your sodium ion with a positive charge, and there are lots of water molecules with the lone pairs. Now, what will happen is that all of them will get together. All of them will get together, and when they get together, they will the positive sodium ion will eventually form or get attracted to these water molecules. So they all get attracted to. So that's bond formation that's happening, right? It's a gaseous ion which is independent, not doing anything. It's not making any bonds, and it eventually forms bonds with water molecules. So since only bond formation takes place in this case, only attractive bonds or attractive forces are formed. Hence, it's always exothermic. You guess this part clear, that it's always exothermic, enthalpy change of hydration.
Yeah.
And when you get stronger bonds, well, what if you have a higher charge density on the ion? So if you have a higher charge density, that means even stronger attractive forces. That would make delta H hydration even more exothermic. When you have higher charge density, you have higher charge density when you have smaller ions. Or you've got greater charge. ठीक है, brother, is this clear?
Yeah, that's clear.
Remember, smaller ions with greater charge, they're going to attract water molecules more, and they will have a much bigger hydration enthalpy. And that's it. That's with the definition. ठीक है, that's enthalpy of solution, and you've got enthalpy change of hydration. So we're going to move towards the Hess cycle that will. So this Hess cycle for enthalpy of solution. So now what this Hess cycle will do is that the Hess cycle, and this is only for ionic compounds. Now in this Hess cycle, you've got two things. One is that you've got enthalpy of solution, which is what it's. Let's say I've got NaCl solid plus aqueous, and it's going to dissolve, and it's going to turn into aqueous ions. So it's going to become Na+1 aqueous and Cl-1 aqueous. Now that's your enthalpy of solution. Now to dissolve this salt crystal, okay, imagine this crystal where you got positive and negative ions all grouped together. Okay, तो ये आपका एक ion हो गया. So you're going to have a bunch. So you're going to have a bunch of these sodium and Cl ions. All attracted to each other, all very strongly ionically bonded to each other. Now, when you want to dissolve a crystal in water, the first thing that needs to happen is that you have to break the crystal. That's why you stir vigorously. When you stir vigorously, the ions, they dissociate. They turn into gaseous ions. Which simply means that you got the same thing. As it simply means that so it means that you got the same thing, except that hold on one second. Except that the ions are no longer together, but they are gaseous. So you've broken the ionic bonds. Okay, so the ions are no longer, they're just moving about freely. So they've turned into gaseous ions. And that's so what is this step, by the way, Ska? What is the name of this step? This one. इसको क्या कहेंगे? You've got an ionic lattice and you've broken the lattice and turned it into gaseous ions. So what is that called?
Is it vaporizing?
No, that's the opposite of lattice energy. That's the negative of, or the, because you're going in the opposite direction. Lattice energy was what? It was when you had gaseous ions and they would form the ionic lattice, right? Now you're kind of doing the opposite, going in the opposite direction. Okay, is this clear?
Yeah.
So that was lattice energy. This is actually, in fact, endothermic. This is where you vigorously stir the salt in water. And the purpose
So
of
this step is called lattice energy,
no,
or is it the opposite of?
it's the opposite or the reverse of lattice energy or negative of lattice energy. ठीक है, clear है?
Okay, so then vaporizing is what then?
It's
What
vapor.
is?
It's vaporizing. It's vaporize. Enthalpy of vaporization is when you turn liquid into a gas.
Okay,
In that you
that
don't
makes sense.
actually break bonds. You just break the intermolecular forces if it's a covalent molecule.
Okay.
So you're breaking the lattice instead of forming the lattice. So this step is endothermic. And then you have these gaseous ions. What do? You take these gaseous ions and you turn them into aqueous ions, which I did show you over here. Okay, what you're going to do is when you stir, you break the lattice by stirring, and as soon as your lattice gets broken, so as soon as your lattice gets broken, it gets surrounded by water molecules. Okay, that's the whole process of dissolving. Okay, you take a tiny NaCl crystal, stir vigorously, you break the lattice, you provide the energy to break the lattice, and as soon as the lattice gets broken, the ions they attract water molecules and they get completely surrounded by water molecules. Okay, the same exact thing will happen with the negative ion as well. Okay, so if I have a negative ion, it's also going to be surrounded by water molecules, except the positive H in the water molecule, the partial positive H, that's the one that's going to get attracted to the you get water is a polar molecule, so some part of it will get attracted. And what is this step? This is enthalpy change of hydration. And that step is exothermic because you're forming bonds. Is that clear?
Yeah, that's clear.
So basically, we dissolve something, you break the lattice, and then you expect the ions to form bonds with water molecules. So when does something not dissolve? It's not going to dissolve if either the lattice is very strong. That means you're not able to break the bonds. Okay, that's what happens with marble. Marble does not dissolve because the positive and negative ions in marble are like really strongly attracted to each other. So no matter how much you stir, you'll not enough. There's not enough energy to go about breaking the lattice. The other part is that maybe the lattice breaks down. Okay, maybe it does break down, but it does not attract the water molecules. So if it's not attracting the water molecules, it's not going to get surrounded by water molecules. So most likely it's going to go back. The ions are just going to end up together again and they'll form the lattice back again. So no matter what amount of stirring you do, maybe temporarily the lattice breaks down, but since it's not attracted to the water molecules, this step does not happen. It just goes back and forms the lattice back again. That's it. So nothing overall happens in that case as well. Okay, so is this clear that both things need to happen? Clear?
Yeah.
So your equation is basically what enthalpy of solution is basically equal to what? It's the negative of the lattice energy plus the enthalpy change of plus the enthalpy change of hydration. You have to get the moles correct because sometimes there will be 2 Cl ions, sometimes there are going to be 3 Cl ions. So you have to get the moles, but that's the overall general equation for enthalpy of solution. One thing about this equation is that the first part is actually endothermic because you're breaking the lattice. And the enthalpy of hydration part, which is positive in the equation, is actually in fact negative because it's exothermic. Okay, so the signs in the equation are actually, I mean, in reality, it's the opposite. Okay, is this clear? You clear?
Yep, it's clear.
So now the other thing about this is that there'll be two questions. There's going to be a qualitative question where they're going to ask you to justify or explain. So explain why solubility of group 2 hydroxides increases down the group. So increases down group 2. So if you look at group 2, it's what it's the first one is magnesium hydroxide, not very soluble. Calcium hydroxide, strontium hydroxide, and you've got barium hydroxide. So the first one is basically the solubility increases. So the first one has a pH it's not very soluble, so the pH would be around, if you mix it in water, it's going to be between 7 to 8. The next one would have a pH of, let's say, 10. And so on. The last two will probably have a pH of, they're very soluble, so the pH would be around 12 to 14. Okay, so the solubility increases. Now you have to explain why the solubility increases. So what you're going to write is that if the solubility is increasing, तो पहले तो मुझे explain करो कि which part is going to be bigger? Will the if the solubility is higher, is breaking the lattice going to be easy or more difficult? क्या होगा out of the two?
Easier.
Easier. And will it attract the water molecule strongly or weakly if it's soluble?
Strongly.
Strongly. So basically that means that overall it's becoming more exothermic, right? This becomes greater, while this becomes easier, so it becomes smaller, right? So that's the idea. Vice versa, if solubility decreases, less soluble, that means the lattice is becoming stronger. You need more energy to break the lattice, and the attraction with water decreases, so less energy is given out, right? So that's the basic idea. That so if the solubility increases down the group, so here's what you're going to write, that when you move down the group, the cationic radius increases. I mean, the anion is the same. I mean, everywhere it's OH ions, so the cationic radius increases. As they increase, so if the ion is bigger in size, that means both lattice energy and hydration, they both decrease. So when you're moving down the group, the radius is bigger, so they're going to form weaker bonds. I mean, all their bonds are going to be weak. Bigger ions, they always form weaker bonds. So whether you're breaking them or whether you're forming them, the bonds are weaker, which means that lattice energy and enthalpy of hydration both are going to decrease. Okay? Is this part clear as well?
Yeah.
अच्छा, इसके बाद ये कि so both of them decrease, right? But since the solubility is increasing, so that means the exothermic part is actually becoming bigger. This was the exothermic part. The first part was the endothermic part. But delta H lattice energy decreases more because it's becoming more soluble down the group. So that means breaking the lattice is becoming easier or relatively easier, decreases more compared to delta H hydration. Hence, overall delta H solution becomes more exothermic. Or we can say, or less endothermic. And hence the solubility increases. Is that clear?
No, I don't really understand the last part.
See, I told you both of them are decreasing, right? You got down the group, when you move down the group, the ion size becomes bigger, right? Bigger ions, they form weaker bonds, right? So you're breaking and forming weak bonds down the group. So that means if you're breaking and forming weak bonds, that means you're breaking a lattice that is weak. You're forming bonds with water that are also weak. So that means both of them are decreasing, right? That part clear, right? Both lattice energy and enthalpy of hydration decrease, right? Is that clear?
Yeah.
But since the solubility increases, that means when does the solubility increase? When the endothermic part, when you're breaking the lattice, it becomes easier to break the lattice. Then the substance will be more soluble, right? Is that clear?
Yeah.
So that means down the group, breaking the lattice is becoming even more easier compared to this one. So lattice energy decreases more compared to enthalpy of hydration. Does that make sense now?
Yeah, that makes sense.
Okay, so or you could have so this decreases more and enthalpy of hydration. So the bonds that are formed with water, relatively speaking, they're stronger compared to the bonds that are being broken. Because this statement means this thing. Is that clear?
Yeah.
So the other part is you have to write something that's very similar for sulfates as well. Now with sulfates, you've got what you got. As a sulfates are, you got MgSO4, which is very soluble. You've got calcium sulfate that's partially soluble. Then you've got strontium sulfate that's barely soluble, and then you've got barium sulfate that's highly insoluble. Now it's the opposite in this case. So now it's the opposite in this case. Solubility decreases now. So solubility decreases now. The first one is soluble. This one is slightly partially soluble. Uh, and these are insoluble. So we're gonna write something which is going to be kind of the same. Okay, so down the group, the same thing happens. That the cationic radius increases. Bigger ions down the group. So both lattice energy and hydration, they're both going to decrease. But this time around, solubility is actually decreasing. That means breaking the lattice is still, relatively speaking, more difficult compared to this one. Is that clear?
Yeah.
So it's down the group, the solubility decreases. So that means it's harder to actually break the lattice relative to it forming bonds with water. So although both are decreasing, but in this case, the lattice energy decreases less. It's still, the lattice is still pretty strong, harder to break. So, but lattice energy decreases less. Compared to delta H hydration. Hence, the overall enthalpy of solution becomes so what does it become? It becomes endothermic overall, or less exothermic. You have to remember or memorize this. I mean, these statements, TK, every time it's the same statement, except for the last part, which is the opposite in both cases, because solubility increases down the group, solubility over here decreases down the group. Is that clear?
Yep.
So that's it. There's one thing about enthalpy of hydration that just a minor point about enthalpy change of hydration, that for some ions, delta H hydration does not exist, as they end up reacting with water. So instead of getting surrounded by water, they actually end up reacting with water. So one example in this case is, for example, oxygen ion gaseous. You mix it in water, it's not going to just mix in water. It would actually react with water to form what 2OH ion aqueous, right? So just remember that enthalpy of hydration does not exist for all ions. It's something does not dissolve in water, instead reacts in water. So enthalpy of hydration is not going to exist. So that's it. The other part is that you have to do questions related to the same cycle. Let me show you the questions 1 second. Is there? I think it's this one. As the first part, that's CaCN2 with water. So you have to make an equation. So with water, they've given you some statements above. So can you read the above statement? Tell me what the products are. Based on what's written above. Were there any idea?
Um, is it going to be calcium hydroxide?
Yes, the white precipitate is probably calcium hydroxide, and what else?
Um,
I mean, just make a guess. What kind of compound is N going to form?
Is it a nitrogen oxide?
But what's the oxidation state of nitrogen in CH3N2? I mean, it's an ionic compound, right? This is -3 and this is +2, right? So which nitrogen compound do you think has a charge of or oxidation state of -3? I mean, it's going to be NH3. It's NH3 is N is -1. Is that clear? So N is -3. Is that clear?
Yeah. Okay.
So here's your 3-mark question. Typically, he's talking about he's asking you to explain the enthalpy solution. Why does it become less endothermic down the group? So what you're going to write that down the group cationic radius. What happens? Cationic ionic radius increases. So both delta H breaking the lattice, which is lattice energy, and the ions forming bonds with water, that's hydration, they both decrease. But they're becoming more soluble, so breaking the lattice is actually easier. So delta H Le decreases more. Compared to delta H hydration. Hence, overall, your delta H solution becomes more exothermic or less endothermic. TK, is this clear? It's the same question exactly. Is that clear?
Yep.
Can you state the direction of the arrow and what should I write over here? What are you going to label this?
So it would be from gaseous to aqueous.
And what is it called?
Delta H hydration.
Yeah, that's your delta H hydration. What's this part? Ionic solid to gaseous ions, or gaseous ions to ionic solid.
The ionic solid to the gaseous ions and its negative lattice energy.
TK, in this direction, that's your lattice energy, right? And what's the last part? Solid ionic to aqueous ions.
Yeah, delta H solution.
TK, that part is delta H solution. This one is the same question. So here, this one is a much longer question. Plus it involves, this is not really about delta H solution. So we'll do that. We'll do this one tomorrow then, TK.
Okay.
Baki clear, we are done with the chapter. TK, we're done with the chapter. We'll just do more questions and then we'll move on. TK.
Okay.
Okay. Take care.
Okay. Thank you.